AI has cracked a key mathematical puzzle for understanding our world. This just in from MIT Technology Review. And look at this puzzle right here. It's got the bumps, it's got the valleys, the surfaces, it's got the braille, it's got the bits, the ones and the zeros, not only going up and down like in the Matrix, but going in circles. It's got it all. This puzzle is really hard, as you can see, and AI has just cracked it. I'm being a bit hyperbolic, of course. This is actually about a new paper that can numerically solve a particular type of partial differential equations way faster than anything before it. So this is about this new paper, and we'll get into the paper in a second. It's pretty cool. But as you can see, MC Hammer, the infamous MC Hammer, has tweeted this out, and he has actually a pretty cool Twitter feed where he regularly tweets about scientific papers and so on. So pretty cool cross-domain overlap. I recommend that. So we'll get into the paper, we'll get into the code a little bit as well, because I think it helps to understand what's going on. And I want to start out by, this is the blog post by one of the authors, and it's pretty good to get a basic overview of the paper. And here is the motivational example. So the motivational example is the Navier-Stokes equation, which is an equation in fluid dynamics. So you're trying to predict how a fluid evolves over time, given a certain parameters like its viscosity and a forcing function. So basically how sticky it is and how hard you stir it. And then you want to know how it evolves over time. And you can see on the left is given an initial condition, and I think on the right is sort of a rollout after the 10th time step until the 50th time step. And the ground truth is obtained with a sort of classic numerical solver where you do little time steps and you calculate the interactions, and then this takes a lot of time and compute. And on the right is the prediction of this new Fourier neural operator that this paper develops. And you can see it's almost equal, and the gist of it is that the thing on the right simply takes one forward propagation through a neural network. So it takes like 0.00 something of a second to compute the thing on the right, whereas the thing on the left is quite hard to compute and, as I understand, can take minutes. So here you see the motivational example. These things are described by partial differential equations, which are sort of linearized ways of describing how the system evolves over one time step. And it'd be cool if we could solve these faster, because this is applications in aerodynamics and other types of engineering fields. All right, so let's jump into the paper. As always, if you like content like this, consider sharing it out, telling your friends about it, and subscribing, of course. So the paper is called Fourier Neural Operator for Parametric Partial Differential Equations, and it's by Zhongyi Li, Nikola Kovacsky, Kamyar Azizadenesheli, Burigere Liu, Kaushik Bhattacharya, Andrew Stewart, and Anima Anandkumar of Caltech and Purdue University. So I feel the paper is both very cool and a bit overhyped. So we're going to see what it does. It's for a particular type of PDEs, and it has a lot of, let's say, engineering choices that make it possible to solve with neural networks, but also that limit its applicability to where the classical methods would be applicable, where this thing isn't. So there are trade-offs definitely to reach the sort of speed up that they reach, but we'll get into this. First, I actually want to scroll down right here all the way, because there is something that you don't often see in the sort of machine learning field, and that is here in the acknowledgements section. And I just find it interesting. Don't regard this as anyone, but here we are supported by the LWLL grants, which I understand is DARPA, Beyond Limits, which is like makes AI or systems for things like gas and oil and so on, with British Petroleum as a main sponsor. Raytheon, which of course is a giant military manufacturer. We have the Army Research Laboratory and so on. So so you can see that this is kind of, I don't know, I don't see this often. This is sort of a good bouquet of sponsorships. Of course, there's also Microsoft, Google, and so on. Yeah, but it's just interesting to see that the army is pretty heavily into these things, and of course they would be. I mean, rockets need to fly, and they need to be aerodynamic, and so on. So, yeah, I'm not saying this is bad or good. I just thought it was interesting that, you know, Raytheon would be a sponsor of this. All right, so let's dive in. As we said, we're interested in these types of problems right here, where you have this thing called, there's this quantity called the vorticity, which, as I understand, is a derivation of the viscosity. So it sort of tells you how the fluid is moving right now. And so this state right here, and then you apply a sort of constant forcing function, and you want to know how that evolves over time. So you can see at time step 15, you get sort of this picture. So these move past each other. You can see this moves here, and then at time step 20, you can see they are fairly moved. Okay, this blue thing moves in here as well, and they just sort of mix. And there's this, there are certain parameters that make the fluid more sticky or not so sticky. And the interesting regimes is, I guess, when it's not very sticky, so not too sticky, but also not sticky enough. And then these really complicated patterns occur. And to predict them would be very, very valuable. So you want something that takes in this initial state right here and outputs all of these future states. And usually this is done by these classical numerical solvers. So the Navier-Stokes equation is described by a set of partial differential equations, and you can see this down here. So Navier-Stokes equation is described by this set of equations right here. Is there? Yep. And you can see that the this is fairly complex. It includes partial derivatives, gradients, and so on. So this is this vorticity, and it includes that on both sides. And this is two derivatives maybe, or is it just the delta? I don't even know. I'm not an expert in partial differential equations by any means. So anything coming from that direction, don't take me for granted. I'm going to give you sort of the thing of what I understand from this paper. And so with respect to that entire area, I'm not an expert. I just can understand that this is fairly complex. And what you usually do is you take the initial state and you just evolve it in time. So you take this time parameter and you go one little time step. And then you calculate, because these are all sort of linear equations, you calculate this one little time step into the future. You update your state, right? It's sort of like, you have your points here and how they move. And how they move is given by their gradients. So these are all sort of linearized things. Now, you don't want to move them too much per time step, because ultimately, if this thing moves and this thing moves, then the movement of this arrow will change because this thing over here moves, right? So you want to compute this one little time step into the future, like to here and this to here. And then you want to recompute all of these arrows. So maybe now that points a little bit more here and that points a little bit more here. And then you want to update it again. So you have these sort of these numerical solvers that go little tiny time step by little tiny time step. It's not even these, if you see t equals 20 or something, it's not 20 time step for these solvers, but these usually go like 1,000 or 100 steps per time step that is here, or something like this. They need to take very tiny steps to be accurate. And that takes a long time. So the idea is, can't we simply input this, let's say this thing, or like something at time 15, and directly predict the thing at time 30. And that's exactly what this paper does. And a lot of papers have done this before, but without much success. So this paper proposes to do this in the Fourier domain, and we'll see the path that they take right there. So they go into we'll shortly go into sort of the basics right here. So what you're looking for is a function g that takes an a and gives a u. So what are a and u? A and u are both function spaces. So a and u here are functions. So a is a function, as you can see. A is a function and u is a function, but you can characterize them as data points. So in this way, there is a functions and data points are sort of interchangeable. You can see an image like this as a data point where it's an image, but you can also see it as a function where every x and y coordinate is mapped to a value, right? So when they talk about functions, very often they talk about this type of function where you have x, y, and t. So t is 0 here. So the function would x, y, t, map that to some value, right? Here, the vorticity. And you want to transform this function. So this function would be a. A would be the function at time, let's say 0 or something, or the times 0 to 15. You would want to map that to the function u that also takes an x and a y. Let's leave t out for the moment. It also takes an x and a y, and let's say t, but t is set to 30, and maps that to a vorticity, right? So you want to input a function and output a function, but it's the same as inputting an image and outputting an image from an engineering perspective. Of course, from a math perspective, it's a little bit different. But other than that, it's a fairly standard machine learning problem. So you have these sets a and u, and you're looking for this function g that maps a to u. Okay, so we study maps G, which arise as the solution operators of parametric PDEs. Suppose we have observations where A is an IID sequence from probability measure mu, supported on I, and U is the A transported by G. It is possibly corrupted with noise. We aim to build an approximation of G by constructing a parametric map, this G right here. So it's a bit of a mathy way of saying we have a bunch of data points where A, this is the initial state, goes to U, which is the state at some point in time. And we know that there is a function G. This is this G with this inverse cross. We know that there is a true function that maps any A to U. So a single function G that can, if I input the initial state, can give me the output state. And what I want to do is I want to approximate this by a parametric version. So these here are the parameters. And of course, as you can guess by now, G is going to be This G right here is going to be a neural network that is parameterized by theta. So these would be the layers of the neural network. And we're going to input A into the neural network, and we're going to get out U. So that's basically that. There is quite a bit of math right here. And the math here is to derive what they call a neural operator. So here is one layer of this neural network. As we said, we're going to input A. Now A, first thing that we do, A is going to be, let's say, up projected. So A is going to be made into a latent representation V0. So this is, let's call that here, P. So there is a function P, which is going to be a little layer of neural network, and it is going to produce this V0. So V0 is going to be a latent state of the neural network. And then there is going to be a number of these layers that transform this to V1, V2, V3, and I think there are 4 layers of these in their particular implementation, but there don't need to be 4 layers. You can choose that, as you can choose any depth of neural network. And then at the end, you're going to project that down to whatever output you want, so U. Okay, so this function here is called Q. And these are just going to be neural networks. So P and Q are going to be your very, very classic up projections and down projections of data point. We'll get into sampling. Let's go actually right now. So one thing right here, and they stress this, is that they work in function space, right? They don't work on the, let's say, they don't map the data point to the data point. What you could do is simply have like a convolutional neural network, an image to image network, and so on. But what is the problem with that? So if you have your A, which is your initial state, and it has these bunch of fluid things right here, and what you do when you have an image is you sample this, right? You sample this at different, maybe a regular grid. I am terrible at regular. So you sample this into a certain amount of pixels, and your neural network will operate on this, right? This will give you some kind of a tensor, which is, let's say we have so this is a 7x7 grid, okay? So your neural network is going to expect this as an input dimension, and whatever U is, of course, so you map this to U, which is also going to be some sort of image, okay, where you need to output pixels. So again, you have some set resolution, and your neural network can only operate at that particular resolution. What they're doing right here is, the cool thing about it is it can operate at any resolution. So once you've learned the network, you can input higher resolution images, or you can output higher resolution images. Any sort of, you can deal with more resolution, less resolution, sampled irregularly. You can deal with a lot of things once the neural network, their neural network is learned. And how do they do it? They do it by only ever acting pointwise in the spatial domain. So what they're going to do is they're going to take this A, and now we get into the more critical things. So here A and U aren't just the beginning state and the end state. In fact, in this Navier-Stokes example, A is a tensor like this. So A is going to be a tensor with slices, and each slice describes one time step up to a given time. So this here could be t equals 0. So there is kind of the initial distribution, and then t equals 1, and so on, up until t equals like 10, let's say. I think they do 10. So they let this thing evolve for 10 time steps, and I'm going to guess they do it using one of these classical methods, and that's the input. So the input isn't just the initial state. The input is actually, here is what happened in the first 10 time steps, and then the output isn't just the output at some particular time, but the output is actually also a slice right here. A sliced tensor. So each slice here describes the output at a particular time. So this would be t equals 11 up until t equals 50. Okay, so this is u. So the top one is sort of the conceptual thing, but the bottom one is what really happens. So they input 10 time steps and they get out the 40 subsequent time steps. They predict them all at once. Okay, so, and now you can see that in this particular case, how I can understand this is at each pixel here, I want to know what is that pixel's value after like certain amount of time steps, okay? Like 11 or 50 right here, or 40. And of course, the result is going to not only depend on the time 0, but on the entire evolution of time 0 to time 10. So this here is an entire column for that pixel, and this is akin to that particular pixel having this many channels. So here I can just say, well, these are technically 10 channels, or 11 or something like this. I probably screwed up. This should be t equals 0 to 9 and then 10 to 49. But so this is an entire stack. We can interpret this as input channels right here, and we can interpret these as output channels. Okay, so ultimately, one pixel is going to have input channels, all the time steps that happened up until the point where we want to predict, and the output channels are going to be at the same time all the time steps of what we want to predict. Okay, so these projections now, coming back to this, they simply work in the channels. So these P and Q, they are 1-by-1 convolutions. And the 1-by-1 convolutions simply up project and down project these features. You see, these are 1-by-1 convolutions. Actually, they could be dense layers. Let's check that in the code later. But for sure, what they do is they only work pointwise. So they don't mix the individual pixels together. In here, you simply get like a D by D grid with each has 10 channels. And then you simply up project that to, so here you have D by D times 10. And then you up project that using P to D by D times, and here is a parameter that you choose. So this is sort of your latent dimension, okay? And you are going to transform this tensor, keeping it in this D by D by W dimensionality until you back project it using Q to D by D by, in this case, 40. Okay, so, but this and this, they only work pointwise. And that means there is no particular dependence on the D right here. So the next data point could actually have a different D as long as this pipeline right here can handle different dimensions, because the P and Q only act pointwise, you're good. So what do these magic layers here do? So these are these Fourier neural operators. Okay, they transform one hidden state into the next. Note that we have 4 of these layers, so they don't need to be the same as the number of time steps we're trying to predict, you see? And it's pretty clear from here. So these 4 hidden layers, they're simply transforming this entire volume right here, this entire input volume. They are transforming this as a sequence of latent states and then outputting this entire volume. So this down here has nothing to do with the time steps that we're trying to predict. It is simply a sequence of computations, of latent computations. And you know that in a neural network, the deeper you make it, the sort of more complicated functions arise. Even though, of course, the universal approximation theorem says that with one hidden layer, you can do anything. But in general, if you have deeper neural networks, the more you can kind of make more complicated things. And so 4 seems to be a good number of complicated for these particular problems. So here's what one of these layers does. It is very much like a residual network. So here you have V, the V is the hidden representation at t plus 1. And t plus 1 is not, as I said, is not the time step in the Navier-Stokes sense of time evolution of the PDE. This is simply the layer t plus 1. So I don't know why they maybe t here still makes sense. Is it not? Because it's large t. Yeah, so they have large t right here. Okay, maybe, but in the engineering sense it is not. It's simply the layer. And you can see it's formulated as a function. But again, don't be like the x right here. This is simply the x and y and t coordinates. So all of this here can be represented as one big tensor, x, y, t, or x, y channels, or something like this. Okay. Don't be confused by the fact that these are formulated as functions. So what we want to do is we have two different things. So this is one neural network layer. As you can see, at the very end is a nonlinearity. This is a pointwise nonlinearity, and this is in the original pixel space, or in the original spatial space, the d by d space. Each of the things gets a nonlinear function slapped on top, as is normal. Then this part is normal as well. This is simply a linear transformation of the input. Again, this is pointwise. Okay, so this is a linear transformation. Okay, so far so good. We have a linear transformation of the input and a nonlinearity. The important part is this thing here. So what this thing is, this is a kernel function that depends on the initial condition. So not only on the last hidden state, but the initial condition, and sort of is then multiplied by the last hidden representation, like here. And then only x is applied. So notice the difference right here. This is at a point x, we're getting this function value, which means we're getting the entry of that tensor, and then we're applying the linear transformation. Okay, this makes it pointwise. Here, first we compute this function by applying this kernel to the input function, so to the entire input tensor, and only then we are looking for the particular entry. So that means this thing here is a pointwise transformation of that tensor, while this thing here, it takes in the whole tensor and outputs a sort of new tensor. So this is going to be the magic. So here where k, it goes, you can see it goes from a U space to U space, maps to bounded linear operators on U, and is parameterized by theta. Maybe. What's this? I don't know. I never know. So this kernel, we choose this to be a kernel integral transformation parameterized by a neural network. So they define the kernel integral operator as this, and you can see this is an integral over the D. D is the input space of U, and A, actually. So this is a function that's dependent not only on where you are in the tensor, but on the initial input, this A, and then that's convolved. So this here is a integral over the entire space, so that's convolved with V. You can see that this is a convolution, and it's fairly complicated. So this alone tells you nothing, But luckily, they say that they restrict this. So it's a bit annoying when things always depend on this A. And that means that each of these functions right here, each of these arrows right here, these are the neural operators. Actually, let's go here. Each of these Fourier neural operators right here, they would always also depend on this A here, like this, and like this, and like this. This is a bit annoying for deep learning because we sort of want one layer's representation to go into the next one. So they simply make an engineering choice and say, nope, nope, nope. So they say, we impose, right? We impose. If we remove the dependence on the function A, we impose that the kernel is simply a function of x, not only x and w, but only x minus w. So now you have a sort of proper kernel function in there that we can handle. We obtain that 4 is a convolution operator. Okay, it wasn't a convolution before, it was just an integral, but now if you restrict your kernel functions to this, you get a convolution. We exploit the fact in the following section by parameterizing k directly in Fourier space and using the fast Fourier transform to efficiently compute 4. This leads to a fast architecture which obtains state-of-the-art results for PDE problems. So there's quite a bit of math right here to finally arrive at this thing here. So what is all this math for? This math is for saying what we want. We want to build our neural network like this, okay? And what we do is we simplify and specify this kernel thing until the kernel looks something like this. So we restrict the kernel to be a convolution. And since a convolution in Fourier space is just a multiplication, what we can do is, instead of taking the function v and convolving it with this kernel, what we can do is we take the Fourier transform of the function v, then multiply it in Fourier space by this thing. And this thing is now simply a matrix that's learned in as a bunch of parameters. And then we do the inverse Fourier transform. Now you might ask, why is this relevant? Why can't we just do a convolution like we do normally? And the reason is, so when you do a Fourier transform, what do? You have some kind of signal, like and so on. You have a signal, and you transform this into Fourier space. And here we just go like one vector. So here, as you know, in Fourier space, you have these basis functions, which are sort of these different parameterization of sine waves, or you can do it with cosine waves, and they get faster and faster and so on. So you know that you can decompose any signal into its basis functions in this kind of periodic function space. So this function right here, it might have, 1 times this function plus 0.1 times this function plus 2 times this function minus 5 times this function, and so on. So you can describe any of that. Now, for these type of PDEs that we're looking for, the special thing about them is they are fairly well described if you simply cut away the sort of top Fourier modes and only work with these, because they are, sort of the individual tiny ripples you might not want to take into account. So you can truncate the lower Fourier modes. And that's what they do exactly here. And they learn, so instead of transforming this signal directly into the next hidden representation, they go to Fourier space, cut the top Fourier modes. They have a way of making the next representation in Fourier space, and this is this R here, and that is simply a weight matrix that they multiply with, and that is, you can prove that that is the same as convolving in the original space. So multiplying in Fourier space is the same as convolving in the original space, and so they multiply the green numbers right here by R, then you get something out. So I should maybe, this is way too much. So the green numbers you multiply by R to obtain new green numbers. So maybe R is 2, 2, 4. So the new green numbers would be 2, 0.4. Then you do the inverse Fourier transform. So you get back to a signal. Now with 2 times this, so it might be bigger, and 0.4 times, so I can't even draw, but you sort of get the idea. You put it into Fourier space, you apply the function R, which is a multiplying by a matrix that you learn in Fourier space. You get new Fourier coefficients, you map them back, and there you have your next layer's representation. Almost, okay? So this is this Fourier neural operator, and it's described right here. What you do is you take your representation, your hidden representation, you put it through a Fourier transform, which you can do in a differentiable fashion. Right? You get these Fourier modes, which describes how to decompose the signal into these periodic functions. You throw away the top modes, which is your sort of regularization. You apply R, which is a dense layer of neural net. Not even that, it's a multiplication, okay, by a weight matrix. And then you obtain these new Fourier modes. You do the inverse, and then you have the next representation almost. What you do is, we saw this before, a pointwise transformation in the original pixel space. So this is very much like a residual network, right? Residual networks, they also have this. They have the implemented as one-by-one convolutions. And then at the end, you apply the non-linearity. What is good about this? 2 things. First of all, throwing away the top Fourier modes is very advantageous to these types of problems that we have right here. You can see that the little jiggles right here, they will be sort of sorted out by the larger scale movements of the fluid. So throwing away the top modes is a sort of a regularization. It helps with generalization, and it's very easy in Fourier space. So these things, other than natural images, are described well by these Fourier spaces. And that, again, is an engineering choice. So you cannot not apply these things to everything. You can apply them to where this type of assumption holds. Second of all, this is now fully independent of the discretization of the input, okay? Because when I take a picture and I sample it in a 3x3 grid, I can do a Fourier transform and I'll get all of these numbers right here, okay? It's just, the Fourier transform does a good job as possible. When I sample it in a 7x7 grid, like I sample it super densely, I do the same Fourier transform. I get the same numbers right here, okay? And it's not exactly the same. So they always claim it's the same. It's not exactly the same, of course. If you don't sample densely enough, your Fourier transform isn't going to be as accurate, let's say. So ideally, you want the Fourier transform of the real signal, or of the real underlying signal. But since you sample this, you can't have this. So there is a bit of a difference, but it is independent. So that's true. So the function R that you learn simply operates on these Fourier modes, and these are fairly independent of how regularly you sample. Of course, more regular, better, but still fairly independent. So that's That's good. So if you have, what they're going to do is they're going to have something like the 3x3 during training and then sample more densely during inference, which is something you can do, but understand that this is it's just a form of interpolation, right? So the inverse Fourier transform simply gives you whatever you want, interpolating using the Fourier modes it has. And of course, given a certain number of Fourier modes, which is quite small for them, I think it's something like 8 or 12, higher resolution at some point doesn't help you anymore because you've cut off the high resolution Fourier modes. I guess what can help you is this thing right here, but this thing right here only acts pointwise. So you see, this is now fully independent of the discretization of the signal, which is a cool thing. So the two cool things about this entire stuff is that, first of all, independent of discretization. Second of all, these types of problems that we are having here lend themselves very well to be described in Fourier space. So that's why I'm saying this is for a particular type of problem. And also, there are a bunch of other things. You can see right here, you have this entire input tensor right here, and this entire output tensor right here. And these can be fairly large, right? And all the intermediate representations have to be kind of at d by d by w. So this is, you can't go infinite time right here. Like you could with a classic solver, like a numerical solver, all you need is the last time step, right? You go, what's the t equals 1, then at t equals 1.1, 1.2, and so on. You just count up, and you just go always from the last time step to the next time step. Here, since it's a neural network, during training, you need to keep all of these tensors, the intermediate things. I guess you can do gradient checkpointing, but this is engineering-wise, you predict all the future time steps at the same time. So you can't really go infinite in time. And how do you train this thing? You train it by simply giving it one of these A, right? You have a bunch of A's, so you have a bunch of these input tensors, a data set, and where you always say, here is one of these Navier-Stokes equation, type of problems. I've sampled it somehow, and I've let it run for 10 time steps, and then I've let it run for longer, So I let it run for longer, and here are time steps. So this t equals 0 to t equals 9 or 10. Let's go 10. And here is t equals 11 to t equals 50. Okay. So you have a data set, and this data set is fully computed by a classic forward solver. So you can't replace the forward solvers right yet because you need them for generating training data, right? So this becomes your training data, this becomes generally your X, and this becomes your Y. And now you're learning this neural network, this entire thing, to give you X to Y. So you see, you still need the classic solvers to produce the training data. That's the first thing. The second thing is you can pretty clearly see that the good thing is that now we can input any A. So the classic solvers, you need to rerun them for each initial condition. Now we simply train with a bunch of initial conditions, train the neural network to predict what happens then, and then it can generalize to other initial conditions. But you know about generalization that the problem is we can only trust our neural network if the problem we're considering is very similar to what we had in the data set. It doesn't arbitrarily generalize, okay? So that is, it's something to remember. So I said all of these things have trade-offs. Trade-off one, you have to predict all time steps at the same time, which is hard on your memory, right? So it limits the size of things you can do. Trade-off two, you can only really trust your neural network if the problem you're considering is within your data set vicinity. there are other problems that we've mentioned. Problem 3, we've made very specific choices with respect to how our kernel looks, that it's only ever dependent on x minus y, so therefore it is a convolution. There's all these channels, engineering choice. More, you cut off the top Fourier modes, which limits the types of signals you can analyze. The next choice is the number of intermediate computation steps right here, which limits the complexity you can assume, and so on. So there are I'm not saying you don't have choices in the other numerical solvers, you probably do, but just to remember that this is the case. So someone might say, well, can't you just, if you want to predict for longer time steps, you could make this t equals 11 and then simply, not go in slices of 1, but maybe go in slices of 100. So this could be t equals 111, this could be t equals 211, and so on. And that is completely valid. What they actually do is they subdivide the space further. So instead of doing like 40 time steps, they are doing like 80 time steps, but still times 11 to 50, I believe. The problem with extrapolating like this and leaving away time steps is that, see here, you have a supervision signal in your training for each of the times. And it might be that the fact that, time step 15 looks something like this, and I know I'm trimmed to emness. Time step 16 is just like a small evolution, like this, right? It's like a small difference, and it could be that the neural networks, because they don't have internal dynamics, right? They don't internally dynamically simulate this physical system. They simply learn to map things to things. And if they are still related to each other a lot, then sort of they can make sense of it. So if one slice, so this could be the slice 15 and this could be slice 16, if these are sort of related, it can make sense. There is a relation between them. Also, you can implement this as an RNN, and then also from one step to the next, it sort of makes sense. You don't need an internal dynamic simulation. However, if you jump from time step 15 directly to time step 115, right, then it might look nothing like it, right? Because it has evolved so much, and there can be quite chaotic dynamics, and that's the entire problem with PDEs, that the dynamics can be super complicated and not easily predictable. So here you don't really have a relation, right? And so since the neural network doesn't do internal dynamic simulation, it probably wouldn't, I'm going to guess something like this wouldn't work too well. I could be wrong, but I'm going to guess classical solvers are still needed for this type of situation. So that's the other limiting factor, is that you sort of are bound to data samples that can be statistically correlatively predicted from one another without having to do the real physical underlying simulations, though I have been proven wrong in the past. All right, so they talk a bit about how the fast Fourier transform plays into this, and there is actually an interesting thing which we'll see at the code. And then they have 3 examples, like the Darcy-Flow, Berger's equation, and Navier-Stokes equation. And they also do these Bayesian inverse problems, where I believe the what you have is sort of a thing at time step. You have the bottom thing given at some time step, and then you want to find out the original thing. And what you do is you have like an algorithm that is simply guessing. So you have a U given, and you want to find out the A. So the A is unknown. So you simply start with A0 and guess what U is going to be from that A0. So you evolve your state A to U. And then if it's not entirely correct, you try again. You try A1. Okay, what does that give me now? U. So you see, you kind of play a game of guessing, and you have an algorithm that does this guessing kind of smartly. So it says, oh, no, that's not the direction I want to go to. It's sort of a reinforcement learning algorithm a little bit. And the important part is it needs to do a lot of these forward evaluations, right? It needs to change A a little bit and then evaluate and see if the U that comes out is the same as the U that you want. So you want to find the initial state of any given evolved state. And if you need a lot of forward evaluations, it's going to be a problem if the forward evaluation is really slow, like these classical simulators. So these neural networks can really help right here. And I think they bring it down. They bring down the time it takes from 18 hours or so to 2.5 minutes for this entire evaluation. So that's pretty cool. And they also outperform, actually, in terms of error. They outperform these kind of baseline methods. So this is pretty cool as well. So not only are they faster, they also are less error prone. All of this is pretty cool. Now let's just spend like a short time to dive into the code. The code is still quite hacky, but that's research, so deal with it. So here you can see that the top class is what is called this net2d. So net2d, I like to look at the forward pass before I look at how the network is made, because you understand how things flow. So in the forward pass, you simply have this this convolution right here, what's called conv1. It's not really a convolution, right? This is this is simply an instance of this simple block, and x is just passed through it. So this simple block right here, by the way, the data is prepared. As you can see, there is quite a bit of preparation going on. So you have A and you have U. So A, as you can see, is prepared as an S by S, that's the discretization of the grid, by T in. So this is your D by 10, like this is 10 input time steps. And it is already expanded to a T tensor. So the T is going to be the output steps that we're going to consider. So here, A is going to be transformed repeatedly into a tensor that ultimately will have T output time steps. So you can see you have to hold one of these things in memory for each training sample. And then you annotate actually X and Y and T. These are like positional encodings. For if you know transformer positional encodings, these are simply linear positional encodings for X, Y, and T. You concatenate those and off you go. So where were we? X was forward passed through this simple block 2D. What's the simple block 2D? The simple block 2D is this thing right here. So again, let's look at the forward pass. So first of all, we're going to FC0, which what looks like a fully connected layer. We're going to permute the axes. Then we're going to, through conv0, W0, a batch norm, and a ReLU. So you can see this right here is what we saw in the diagram. X1 and X2 are the different paths through the network. This is the top path. If I go back to the paper quickly, this is the top path in this diagram. Okay. And the bottom path is this thing right here. And then the two are added. And then there's a batch norm, which is not in the diagram. And then there is a ReLU. Okay, so the bottom path is pretty simple. And you can see right here, by the way they restructure it, that this is going to be pointwise. So this is not going to be in pixel space. This is going to be a pointwise, only in the channel transformation. So these W's are implemented as one by one convolution. You see, it's a 1D convolution, and the kernel size is 1. So all these does is for each point in the grid space, in the pixel space. For each pixel, they're going to take all of this pixel's channels and transform this into a new vector of the same amount of channels. So you can see the input channels and output channels are always the same dimension. So actually this entire network right here operates on this width, which is this latent dimension. It's only the first layer that transforms this from 13, which is 10 plus the 3 positional encodings, to this latent dimension. And then the last network, this transforms it from the hidden dimension to 128 for some reason, and then 128 to 1, which is each pixel has a one-dimensional output, which is this vorticity that you're trying to predict. And by pixel here, I mean an XYT entry, okay? All right, so, yeah, so exactly. So this goes from 13 to 1, and then it is reshaped again, of course, to the appropriate size to give you all of the outputs. Okay, so you can see this is the input, this is the output down here. In between, we have 4 blocks of this upper path and lower path. So the upper path, the lower path we just saw is a 1-by-1 convolution. And the upper path is this conv0. So this conv0 is this spectral conv3D fast, okay? And it's parameterized by these modes. So the modes is how many of these Fourier modes you want to retain. We saw we throw away the top Fourier modes, whatever they are, and the modes here is whatever you want to retain. In this case, it's set to 4, which is actually 8 if you work it out, and we'll see why. So this spectral conv3D fast, again, let's look at the forward pass. So what does the forward pass do? It does a Fourier transform, a fast Fourier transform. And at the end, it does an inverse Fourier transform. Okay, so this is certainly, we are now in the top part right here. Fourier transform, and at the end, inverse Fourier transform. And now these R in the middle is implemented a bit weirdly, because of how the fast Fourier transform works. What you get, basically you get an image out of it. You get actually a 3D thing, but you get an image, and the important Fourier modes are not like at the bottom or at the top. The important Fourier modes are actually in the corners right here. So what you want to cut away is all of this middle part if you want to throw away. So this is equivalent to throwing away these high frequency things right here. So that's why this is implemented so weirdly. You can see that here. First, we are going up to the modes in each of the X, Y, and T direction. But then we're also going from here, we're going to the last modes in this direction with all the others. This is corner 1, this is corner 2, this is corner 3, and this is corner 4. Sorry, the bottom 2 right here is corner 4. It's a bit weird, and we don't have to actually do this with 8 corners, which you might have guessed, because why don't we do it with modes 3? You see modes 1 and 2, they always appear negative and positive, and you would guess we'd need to do the same thing again with negative modes 3, but we don't, because this thing here is one-sided, which because this is has a property of conjugacy. A lot of these entries of the Fourier transform would actually be sort of symmetric, and the one-sided only gives you one part of these symmetries such that it doesn't waste memory. And it does so for the last dimension. So this dimension right here doesn't have this corner property. It's a bit weird, and you need to know the exact implementation of the Fourier transforms, but you know, that's what it is. So you can see that this mul 3D here is it's compl mul 3D. It simply multiplies the input, which is the signal right here, by these weights. The weights, as you can see, is simply a weight matrix that is in channels, out channels, modes, 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 and 2. 2 because it's complex numbers, and you see in this multiplication that this is a complex number multiplication. So the real part is this, the imaginary part is this, and the operator is an einsum operator. I just thought this was funny. It says bixes, yoxes, boxes. Also I challenge everyone to make Einstein some notation that spell cool words. Bixes, yoxes, boxes. But the important part here is, so A is going to be the signal, which is going to be a batch, in channel, and then XYT. B is going to be the weight that comes in, the weight matrix, which is in channel, out channels, XYT. And you can see pretty clearly in the Einstein notation, or also here, that the input channels are multiplied away. So these are summed over, and what results is the output channels. So this is basically a matrix multiplication for each of the samples in the batch and for each location XYZ. It's a multiplication summing over the input channels, resulting in the output channels. This is pretty standard transform, mapping vectors to vectors. It's complex, it's in Fourier space, but ultimately it's just a multiplication. So this is the code. They simply do 4 of these layers, going to Fourier space and then back again, to Fourier space and then back again. Why do they do this? Because, as we saw, they throw away these higher modes right here, and that also limits severely this applicability. So if you only throw away the higher modes, if you just do everything in Fourier space, you severely limit yourself. In fact, these Fourier methods, they are already not really good for problems that have like non-periodic boundary conditions. So the periodic boundary conditions case is, as I understand, one of the easiest cases. And so the applicability would be limited, and the authors hope that by sort of doing this in the real space all the time, and also having these encoder and decoder networks, that they can retain sort of this informations and be applicable to more than just periodic boundary conditions. Yeah, exactly. And that's basically it. I was ranting for so long. I think we are through to this paper. So maybe a quick summary, because this was a bit of a rant, right? So you want to predict these types of things. These types of things are well described by their Fourier analysis. So transformations in the Fourier domain actually make more sense, because the evolutions of these things is more or less kind of these global signals. It's not localized like natural images, like there's the cat and there's something. This pattern right here, it will repeat, as you go into infinity, these sort of patterns will repeat and repeat. So the sort of global interactions between these periodic signals is much more important. That's why it makes sense to go to Fourier space to transform that. In Fourier space, you can regularize by throwing away the higher modes, and you get the additional benefit that you are discretization independent. So you learn the function once, and then you can input differently discretized signals as you choose, and the function stays the same, because the Fourier transform, it will do as well as it can with the discretization that you give it. Once you're in Fourier space, you simply have a multiplication, and it's actually interesting. The filters here, the author shows some of the filters that are learned. So on top, you see filters in a CNN, and on the bottom, you see these filters, these Fourier filters learned. These are actually, as I understand it, these are transported back to the pixel space so we can understand them. So you can see that the global kinds of patterns that these Fourier operators are sensitive to, compared to the CNN filters, which just have like localize a certain pattern. So this is This is quite interesting. So it makes sense to go into Fourier space. There are a number of trade-offs you have to do. Specifically, you have memory requirements, and you can only predict signals that are similar to what you've seen in the training data set. And you could only solve things with periodic boundary conditions, but by means of architecture of these encoder and decoder networks at the beginning, like the P and the Q, and the fact that you always carry through in a residual way the pixel space signal, makes it such that you might get around this. You might, right? It's not a proof, but there is a possibility that you might get around this. In total, this thing is way faster and more accurate than baselines, and has applicabilities, and is sponsored by the nice people at the military. All right, so this was long, I realize, but I invite you to check it out. The paper is technical, but well written, if you stick this kind of math part out in the middle. It's pretty cool. All right, check out the code, and I wish you a good time. Bye-bye.